In this video, we will be dealing with the West African Senior School Certificate Examination, Part B, that is Essay, Chemistry Paper 2, Question 3 and 6. Before we continue, I want to thank those of you who have taken your time to subscribe to my channel. And for those of you who haven't subscribed to this channel, please like the video, share to other learners, and take some time and subscribe to the channel so that the questions we are going to be solving will come directly to you. But should in case you are facing difficulty in solving some of the problems or some other problem in other past papers, remember that our main goal is to ensure that you succeed in your exams. So channel your difficult question to us, and we will solve them and make them available to you. Thank you. Once more, thank you for taking your time to subscribe to our channel. Let's get started. We are starting with question number 3. Question number 3. 3A. Write the name and structural formula. Write the name and structural formula of one compound conforming to each of the following. Write the name and structural formula of one compound conforming to each of the following. We have 3 general formulas that have been given there. We have the first one, I, is the general formula for alkanes. The second one is the general formula for carboxylic acids. And the third one is the general formula for aldehydes. Now, write the name and the structural formula of one compound conforming to each of the following. Let's take for alkanes. Using the general formula for alkane, and we say N, because alkanes are the number of carbon chains. The number of carbon atoms are numbered. We use N to determine the number of carbon atoms. Let's say N is equals to 1. If we say we substitute N as 1, we will say it will be CH. 2 times 1 plus 2, it will be CH4. That will be methane. If we say it is 2, N is equals to 2, it will be C2. H, 2 times 2 is 4, plus 2 is 6. That will be ethane. So now, since we have been told, write the name and structural formula of one compound conforming to each of the following. The name here will be, for 1, 3A1, where N is 1, the name will be methane, and it will be the compound CH4. Where N is 2, the name will be ethane, and it will be CH3 and CH3. Now let's go to the general formula of carboxylic acid. Now, We have been told to write the name and the structural formula. Structural formula, not molecular formula. Structural formula. So now, if we take n equals to 2, if we take n to be equals to 2 here, it will be Cn, it will be C2, H 2 times 2 is 4, 4 plus 1 is 5. It will be C2, H5, C double OH. That will be, we are not talking of propanoic acid. But to write the structural formula for propanoic acid, this is what you will have. It will be propanoic acid, where N is equals to 2. This will be the structural formula for propanoic acid. This is a structural formula. There is a difference between displayed formula, skeletal formula, structural formula, and molecular formula. Okay, let's proceed. The other one, the general formula for aldehydes. Let's say N is equals to 2. Let's say N is equals to 2. Okay, we will have, because we are just giving an example, one compound. We have not been told to use N. You can use N equals to 1. You can use N equals to 3. You can use N equals to 4, any number. But I have decided to use N equals to 2, one of the lowest. Okay, if we use N equals to 2, it will be C2, H5, CHO. And that is propanol. And if we want to write the structural formula for propanol, this will be what you will have. It's an aldehyde, where N is equals to 2. 3b. Give one test for unsaturation. What is unsaturation? We are talking of alkenes. We are also talking of alkynes. One test for unsaturation. The common test we usually use for the unsaturation is the use of bromine water, reacting bromine water with alkane. So this is what I have for you. This is what I have for you. Addition of bromine water. Bromine water is bromine in tetrachloromethane. So addition of bromine water into a solution containing an alkene. The alkene will turn bromine water colorless, or you can say it will decolorize it, as the bromine reacts with the carbon-carbon double bond. So when the bromine is reacting with the carbon-carbon double bond, the color will now change. The color of the bromine water will now change. It will be decolorized. Once more, I said addition of bromine water into a solution containing an alkene. The alkene will turn brown. It will turn bromine water colorless. It will turn the bromine water colorless, or what we call, it will decolorize it, as the bromine reacts with the carbon-carbon double bond. The carbon-carbon double bond is the unsaturation we are talking of. Okay, let's proceed. Let's proceed to the other one. Okay, B2. Consider the following compound. Consider the following compound. This compound, as you see like this is what we call the displayed formula. This compound where the atoms are displayed, all the atoms in a molecule are displayed. We call this type of compound, this type of structure here, displayed formula or displayed structure. Do not be confused with structural formula and a displayed formula. This is a displayed formula. What I was giving you is the structural formula. How the atoms are arranged. So this is a displayed formula. So the question reads: consider the following compound. This compound here, we have CH3, CH2, carbon, triple bond, carbon, and CH3. Write one. The question is one. Write the IUPAC name. IUPAC is International Union of Physical and Applied Chemistry. Write the IUPAC name for this compound. The IUPAC name for this compound, I'll look at it. The first thing in nomenclature, in our video, our video for nomenclature of organic compounds, you will see how you can name them. This is the first carbon, this is the second carbon, this is the third carbon, this is the fourth carbon, and this is the fifth carbon. Okay, the name for this compound B1, the name for the compound B1 is pent2-ine. Pent2-ine. This is the first carbon, and this is the second carbon. The triple bond is first attached to the second carbon atom. And the parent name is what? The parent name is derived from the number of carbon atoms. The longest chain is derived from the longest chain. Of course, there's no branching here. We cannot talk of branching here. The longest this is the number of carbon atoms here are 1, 2, 3, 4, 5. 5 carbon atom. You know that there is methane, ethane, propane, butane, and pentane. Pent stands for 5. But for its alkanes, we say pentane. For alkenes, we say pentene. For alkyne, we say pentyne. And the short form, we say but pent. We say pent, then we put the number. We put the number where the functional group, because the functional group is alkyne. Alkyne is usually, the suffix is -ine. Just as the suffix for alkene is -ine. Just as the suffix for alkane is -ane. So the suffix for here, the suffix here is what? Is -ine. And the carbon atom where -ine is at the functional group is attached is a second carbon atom. So for that case, we say pent, then we put the second the number of we put the number of carbon the number of the carbon atom where it is attached, pent2, then we attach the suffix. The suffix comes but from the functional group, pent2-ine. So our name there is pent2-ine. Okay, let's go to the next one. State the product of its complete hydrogenation. Complete hydrogenation. What is hydrogenation? Addition of hydrogen to an unsaturated compound. Alkyne is an unsaturated compound. Alkanes are unsaturated compound. So all of them will undergo hydrogenation. So when we add hydrogen to them, we make them to be saturated. We are converting them from unsaturation to saturation, unsaturation to saturation. So in that case, they state the product of its complete hydrogenation. It will not change, but it will change but to an alkane. We are converting an ine to an alkane. So the product of it will be pentane. It will be pentane, and this is the hydrogenation equation. For the purpose of revision, this is the equation. This is not required in the answer, but this is the answer in yellow. In green is only for the purpose of your revision for subsequent exams. Okay, 3. Let's go to 3. The third one is why does it not give a precipitate with precipitate with ammoniacal silver nitrate, whereas some homologous do? Why does this one not give a precipitate with ammoniacal silver nitrate, whereas some homologous do? Very good. Now, it should be recalled that this one will not give precipitate. Now we can now differentiate between terminal and non-terminal. Terminal and non-terminal alkynes. So this one, as you see, this compound, as you see, is not a terminal alkyne. Pent2-ine is not a terminal alkyne. So the answer you can give for this question is that because pent2-ine is not a terminal alkyne, or because pent2-ine is not a terminal alkyne, because pent2-ine is not a terminal alkyne, only terminal alkynes such as pent1-ine will react with ammoniacal silver nitrate to give a white precipitate. Only terminal alkyne such as pent1-ine will react with ammoniacal silver nitrate, that's the toluene reagent, to give a white precipitate. So that is the reason. This one is non-terminal, so it cannot give precipitate. Okay, I hope you've understood it. Why does it not give precipitate with ammoniacal, whereas some do? Because it is not because pent2-ine is not a terminal alkyne. Finish. C1 is write an equation for the reaction between propanol and sodium. Propanol and sodium. An equation between propanol and sodium. When propanol react with sodium, we will have sodium alkoxide. It's a sodium alkoxide, but in this case we have it's a propanol, so it is sodium proposite and a hydrogen gas that is being released. That is the equation. Now we go to C2. C2. State the reaction condition. State the reaction condition for the conversion of ethanol to ethyl propanoate. Ethyl propanoate is an ester. Ethyl propanoate is an ester that is formed from ethanol and propanoic acid. So state the reaction condition. The reaction condition are 1. The reaction condition for C1 for C2 above are 1. First of all, the examiner wants to know whether you know what is ethyl propanoate. And the examiner wants to know what is also added to ethanol to give you ethyl propanoate. So those are the reaction that the examiner wants to know. So what you will do is mixture of ethanol and the propanoic acid is heated under reflux with concentrated sulfuric acid as a catalyst. A mixture of ethanol and the propanoic acid is heated under reflux with concentrated sulfuric acid as a catalyst. That's all. Okay. C3. Mention one reagent that can convert an alkanol to an alkanoic acid. A reagent that we can convert an alkanol to alkanoic acid. What reagent can you use to convert alkanols to alkanoic acid? The reagent is acidified potassium dichromate. It's a strong oxidizing agent. This is a strong oxidizing agent. Or acidified potassium manganate 7. So more preferably, I would like you to use acidified potassium dichromate 6. Okay, D1. D1. The equation below represents one of the reaction of alkanes. One of the reaction of alkanes. This is a long alkane, a big alkane, a long chain alkane, which is broken down into alkene, which is ethene, and an alkane, and another compound X. Determine the formula of X and the homologous series to which it belongs. Okay. If you look at this, the carbon are okay. The carbon atoms are 17. 3 plus 8. Carbon atoms here are what? The carbon atoms here, 2 times this is 6. 6 plus 8 is 30. 6 plus 8. 6 plus 8 is 14. So we need 3. So now, what is now the value of X? What is now the value of X as an equation? So X is what we call, we need 3. There are 3 other compounds here that we need to add to give us this. So it will be, the compound will be what? The compound will be a 3-carbon compound. It is not an alkane. It is not an alkane, but it is an alkene. And it is prop 1-ene. Prop 1-ene or propene. And the homologous series it belongs to is what? Is an alkene. So, it's an alkene. So now, this is an alkane, propane. Now, determine what type of reaction does the equation represent? Breaking large chain molecules into smaller ones, What do we call that? It is cracking. We can use a catalyst, or we can use high temperatures. In terms of catalyst, we can say catalytic cracking. If we are using high temperature, we can say thermal cracking. So this type of reaction is called cracking. It could be thermal or it could be catalytic. 3. Calculate the volume of ethene at standard temperature and pressure that would be obtained from 0.1 mole of this in the reaction. This is the reaction. This is a ethene molecule that is being produced. Calculate the volume. Okay, I get it back here. Now, this is the molecule that has been broken down into alkene and alkane. Now, we want to calculate what volume of this is produced from this. This is still stoichiometry. Here is 1 mole, and here is 3 moles. 1 mole of this molecule is producing 3 moles of this. So we can say, if 1 mole of C7H36 gives 3 moles of ethene gas, therefore 0.1 mole of this molecule that we're told 0.1. Calculate that 0.1 mole of C7. Okay, therefore 0.1 mole of C17H36 will give X mole ethene gas. Solving for our value of X, our value of X will be what? Our value of X will be 0.1 times 3. 0.1 times 3, we will have what? 0.3. 0.1 times 3, we will have 0.3. It will be 0.3. Yes. X is 0.3. X is 0.3. I can now say X equals to 0.3 moles ethene. X equals to 0.3 moles ethene. Then the volume of ethene, what will be the volume of ethene? The volume of ethene will be what? Since 1 mole, according to the standard temperature and pressure, 1 mole of a gas occupies 24.4 dm cube. 1 mole of a gas at standard temperature and pressure will occupy 22.4 dm cube. Therefore, 0.3 mole of the gas will occupy what at that standard temperature and pressure? It will be 0.3 times 22.4 dm cube, which will be 6.72 dm cube, or 6720 cm cube. And that is it. Thank you very much. Thank you very much for that. Once more, for those of you who haven't subscribed to this channel, please like the video, share to other learners, and take time and subscribe to the channel. We are moving to question number 6. Question number 6. State Gay-Lussac law of combining volume. Gay-Lussac law of combining volume. Then after stating it, 2. The following reaction occurred when 100 cm cube of carbon-2 oxide, that is carbon-2 oxide is carbon monoxide, was burnt in 70 cm cube of oxygen. Calculate the total volume of gas mixture in the reaction vessel at the end of the reaction. Volume of gas in the reaction vessel. Volume of gas in the reaction vessel. So now, Gay-Lussac law states that Gay-Lussac law of combining volume states that when gases react, they do so in volumes which bear a simple ratio to one another and to the volume of the product formed if gaseous, provided the temperature and pressure remain constant. Once more, when gases react, they do so in volumes which bear a simple ratio to one another and to the volume of the product formed if gaseous, provided the temperature and the pressure remain constant. Okay, now we have to calculate the volume in the reaction mixture. Okay, this is the reaction that we're given. Carbon monoxide plus oxygen to give carbon dioxide. Okay, according to this law, when gases react, they do so in volumes. Which bear a simple ratio. Okay, the simple ratio here is what? These are how many volumes are here? We are not going to go into moles. We are now going to be using moles in the. We are going to be using volumes in place of moles. We are going to be using volumes in. We are going to be using volumes. We are going to be using volumes in place of moles. Here you see that there are 2 moles of carbon monoxide, 1 mole of oxygen, and 2 moles of carbon dioxide. But since the Gay-Lussac law of combining volume states that when gases react, they do so in volumes which bear a simple ratio to one another and to the volume of the product, provided if gaseous. Okay, now, instead of moles, we are going to use but volumes. Following this equation here, 2 volumes of carbon monoxide are reacting with 1 volume of oxygen to produce 2 volumes of carbon dioxide. We were told And the simple ratio is what? 2 to 1. The simple ratio is 2 to 1. Now, we were told 100 cm cube of carbon monoxide reacts with 70 cm cube of oxygen. Okay, in order to have what is one volume, because we have just learned here that 2 volume here will give 2 volumes here react 2 volumes to the ratio 1 volume. So if 2 volumes, the 2 volumes here, if the 2 volumes here are equal to 100 cm cube, if the 2 volumes here are equal to 100 cm cube, therefore 1 volume will be equal to what? 1 volume will, making x the subject, 1 volume will be equal to 100 divided by, x will be equal to 100 divided by 2. 1 volume will be equal to 50 cm cube. Why do I do this? Is because if we were to say 2 volume is 100, then 1 volume is 70, the ratio is not going to match. So after putting the reaction volumes according to Gay-Lussac law, then the simple ratio we are going to do check now is we want to look for 1 volume. Okay, using the volumes that were given as 100 reacting with 700, as reacting with 70 cm cube, we make our simple proportion. If 2 volumes can give us 100, therefore 1 volume will give us what? It will give us 100 divided by 2, which is 50 cm cube, as I mentioned. Now we now know that 2 volume is equal to 100 and 1 volume is equal to 50 cm cube. So we can now solve our problem now. Now 2 volumes of carbon monoxide. Okay, 2 volume of carbon monoxide to the ratio of 1 volume of oxygen to give 2 volume of carbon dioxide. Now 1 volume is what? Is 50 cm cube. If there are 2 volumes here, 1 volume is 50 cm cube. If there are 2, we now say it is 2 times 50, which is 100 cm cube. Now, for oxygen, it is 50, based on this calculation. For oxygen, it is 50. Then it is 50. Then the total will be 100. Looking at this reaction here, you will see that the total gas mixture for reactants, the total gas mixture in the reaction vessel will be what? The total of the carbon monoxide and the total for oxygen. The total for oxygen is 50, which will be equal to 100 plus 50. It will be, the reaction mixture will be 150. The reaction mixture is not 170. The reaction mixture is not 170 in the reaction vessel. It is 150 based on the Gay-Lussac law that we have stated and we have used in calculating for 1 volume. Okay, we now move to the next question. The next question will be B. List 2 uses of sulfuric acid. List 2 uses of sulfuric acid. The 2 uses of sulfuric acid. B1. Sulfuric acid is used for making detergents. Sulfuric acid is used for making fertilizers. Sulfuric acid is used for making paint, dyes, and synthetic fibers. Sulfuric acid is also used for making salt, what we call sulfate salts. Sulfuric acid is used as acid in car batteries. It is used as acid in car batteries. You check your car, you can refill it with the acid. will be sulfuric acid. Okay, question number 6b2. B2. Give equations. Give equations and the reaction condition for the following conversion. Equation and reaction condition for the following conversion. Okay, 2. Okay, now converting this to this. This is the equation. This is the condition here is thermal decomposition. Zinc carbonate will undergo what we call calcination. Heating zinc carbonate. The process is called calcination, and the zinc oxide will be formed and carbon dioxide, and we call it thermal decomposition. Then the second one, converting this to this. The reaction condition is we will react zinc oxide plus dilute sulfuric acid to have zinc sulfate and water. I said add solid zinc oxide to dilute sulfuric acid in a beaker until it will no longer dissolve. That's when you can have the sulfate. For revision purpose, if you want to make crystals of this, you can say filter off the excess solid, make pure crystals of zinc by crystallization. That is by heating to evaporate the water, washing the crystal with distilled water, and drying in a low oven. Finish. So this is the equation, this is the reaction condition, this is the equation, and this is the reaction condition. Okay, let's go to 3. State how each of the following can be obtained from zinc sulfate. How you can obtain zinc sulfate solid from zinc sulfate aqueous, from aqueous zinc sulfate or zinc sulfate solution. How you can obtain zinc carbonate from zinc sulfate solution. Okay, that's 10. All these are 10 marks. So what you need to do is 3. 1. How to obtain zinc sulfate from this one. The method you are going to use here, this is what we call this, how you can obtain the solid from the solution. How to obtain solid to solution from the solution. We'll do what? We will crystallize. Is by crystallization. How you can turn the solid, the liquid to be the solid. In other words, somebody can say how you can obtain zinc sulfate crystals from zinc sulfate solution. So it is by crystallization. The method is crystallization. And this is how it goes. The aqueous solution of zinc sulfate is heated in an evaporating dish until about half of the water has been removed. 2. The hot saturated salt solution is allowed to cool down, forming crystals. 3. The salt crystals are then washed with cold distilled water and are dried in a low oven to obtain pure crystals of zinc sulfate. That is how you can obtain crystals of zinc sulfate from solution of zinc sulfate. 2. How to obtain zinc carbonate crystals from zinc sulfate solution. Okay, the method here is mixing solution of 2 soluble salts. You are going to make solution of 2 soluble salts to obtain an insoluble zinc carbonate salt. Procedure, this is how you do it. Use a beaker to mix solution of either sodium carbonate or potassium carbonate or ammonium carbonate. All these are soluble salts. I say use a beaker to mix solution of either sodium carbonate, potassium carbonate, or ammonium carbonate with solution of zinc sulfate. When you do this, you will have zinc carbonate and there will be a salt that is also produced. So, for instance, if I should take sodium carbonate, I mix a solution of sodium carbonate and a solution of zinc sulfate. and then mix them, we are going to have zinc carbonate and sodium salt. And how do you obtain the sodium carbonate? This is how you are going to obtain this one. After mixing this, they precipitate. They are solid. That's why they are precipitate. These are precipitate that are being formed. Zinc carbonate are precipitate that are being formed. So in order to make this solid, in order to crystallize this or to make this solid, what you are going to do is the precipitate of zinc carbonate is filtered off and washed with distilled water and dried in a low oven to obtain dry and pure crystals of zinc carbonate. Full stop. C. The C part of the question. The C part of the question reads. The C part of the question reads. Give the reason for each of the following. Graphite is soft, while diamond its allotrope is hard. Graphite is soft, while diamond its allotrope is hard. Sodium salt cannot be prepared by double decomposition. 3. Sodium carbonate, which is a salt solution, turns red lemons blue. We will have to give reason. The first reason that graphite is soft, while diamond its allotrope is hard, is because of the forces of attraction in the molecule. The forces of attraction in the molecule. C1. Graphite is soft. Meanwhile, diamond, which is its allotrope, is hard because the weak van der Waals forces between the layers in graphite allow the layer to slide over each other. That is why it makes it to be weak. The most important thing is the weak van der Waals forces holding the molecule together. In graphite, you can say graphite has weak van der Waals forces holding the molecule together. While this one the forces here are strong. So what I wrote to you was graphite is soft because the weak van der Waals forces between the layers allow the layers to slide over each other. Whereas diamond is hard because all bonds in diamond are strong and directional. The second one is sodium salt cannot be prepared by double decomposition. Sodium salt cannot be prepared by double decomposition. The reason is this: because sodium reacts violently with water. Sodium reacts violently with water. That's the main reason. Then 3, sodium carbonate. Sodium carbonate turns red lemons blue. Sodium carbonate turns red lemons blue. Why does sodium carbonate turn red lemons blue? Give a reason for that. Sodium carbonate, which is a salt solution, turns which is a salt solution, turns red lemons blue. Why does sodium carbonate solution turn red lemons blue? Sodium carbonate, which is aqueous, that is the solution, turns red lemons blue because this is a basic salt. This is a basic salt solution. This is a basic salt solution this is a basic salt which, when dissolved in water, forms carbonic acid and strong alkali, that is sodium hydroxide solution, which makes the solution alkaline. In other words, you can say sodium carbonate is alkaline. Sodium carbonate in water, when sodium carbonate dissolves in water, it forms a strong alkaline solution. When sodium carbonate dissolves in water, it forms a strong alkaline solution, that is the sodium hydroxide. So that is an alkaline. What is the effect of alkaline on red litmus paper? Alkaline solution will turn red litmus paper blue. So if sodium carbonate is dissolved in water, it forms a strong alkaline solution, which is sodium hydroxide. And sodium hydroxide solution will turn red litmus paper blue. So when this is dissolved in water once more, it forms a strong alkaline solution. Okay, 6.1, 6D1. 6D1 is mention two types of curl. Two types of curl. I have three for you. I have three for you. D1, I have three for you. There are three types you can choose from this. The first one is anthracite. That is the first type of curl. The second one is bituminous. Bituminous. Bituminous is another type of curl. And the last type of curl is lignite. Lignite is another type of curl. So if you can mention any two of these, then you have all your marks. Finally, the last question is, name the process by which benzene is obtained from coal tar. Name the process by which benzene is obtained from coal tar. The process by which benzene is obtained from coal tar is fractional distillation. Fractional distillation is fractional distillation. Okay, for revision purpose, we have just named it. It is fractional. The process is fractional distillation. For revision purpose, this is how benzene is obtained. During fractional distillation, coal tar is heated. Coal tar is heated and distills away its volatile compounds. Know that in coal tar there are volatile compounds. So when it is heated, the volatile compounds will escape as gases or as vapor. Vapor. So during distillation, coal tar is heated and distills. It is heated and distills away its volatile compounds, such as benzene, toluene, xylene, at a temperature range of 350 K to 443 K. These vapors are collected at the upper part of the fractionating column. All these vapors like this, they are collected at the upper part of the fractionating column. So that is how benzene is removed. Thank you for listening. Once more, as I said, our main goal is to ensure that you succeed in your exams. So, should in case you are facing difficulty in solving some exam question, please do not hesitate to contact us. Send us the questions, and we'll solve them and make them available to you prior to your exams. Thank you very much. For those who haven't subscribed to this channel, please like the video, share to other learners, and take some time to subscribe to our channel so that all the questions we are going to be solving will come directly to you. Thank you very much.